This is an example of a tensile specimen here, and this was screwed in and they pull it, and you see this one hasn't broken yet, but it's starting to neck there in the region there. That's the weakest region there, and it starts to neck, and eventually it will break apart. And what you do to calculate the stress in the material, okay, which is called the tensile stress, sigma, that's the load P divided by the original area. Now, the original area is just the diameter here of the middle here, what you had in the middle, okay? And to calculate that stress, they just, they do just the rho divided by the original area is quarter pi d squared, which is the original diameter squared. They call that the engineering stress, which is really incorrect if you think about it, because that area is getting smaller and smaller, right? But to simplify things, we use that engineering stress. There's another thing that's called true stress, but in the true stress, you have to divide by the instantaneous area. You constantly have to keep track of what that diameter is, but that's a more time-consuming process. And so we don't use that. And also, that material is getting longer and longer, right? If you put a mark here originally here, and right there, and let's say between those marks it's 2 inches, well, that material will start to strain, elongates, becomes longer, right? And you can show the engineering strain that's called epsilon, which is the delta L, the change in length divided by the original length, okay? And that's the way we're going to plot the engineering stress versus the engineering strain. And materials will go through an elastic deformation process, and they will go through a plastic deformation process. Elastic deformation is just like a rubber band. If you have a rubber band and you pull on it, it goes back to its original dimensions, right? When you apply an initial force to a material, and if it's a small force, it goes right back to where it was. Let's say if you had to mark it 2 inches, it goes right back to the 2 inches. Right? Plastic deformation, that's permanent deformation. If you take it beyond what they call the yield point, then the material starts to yield. It starts to permanently give. Okay, so permanent deformation takes place. This here is an example of the engineering stress versus the strain diagram. And then over here you see the stress, that's plot here. And then over here we'll see the strain here. Now, going back 1 second, what do you think the units of stress are? What do you think the units are if you had the metric system? What is the unit of load? Force. What's the unit of force?
Newton.
Newtons, and the unit of area is meters square, right? Or, so Newton per meter square, we call that a Pascal, right? So now we use usually megapascal, 10 to the 6th Pascal, kilopascal, 10 to the 3rd Pascal. But you always have to have the units displayed on any graph, right? You can't have a graph without at least defining the units. Now the strain, actually the strain, what kind of unit would that have? Well, you have the change in length divided by the original length. So what kind of unit does it have? It doesn't have a unit, right? We usually say inch per inch, 0.002 inch per inch. That means for each inch of length, it changed 0.002 inches. So, or millimeters per millimeter, whatever you want to use. Right? And then over here, this is a typical curve here, for a steel, for a carbon steel. This is the kind of curve that theoretically, according to the books, you get that. Now, this is going to be interesting to see. I'm really actually I was thinking about that last night when I was looking over this. Are we going to see this? Because you see here for the carbon steel, you see here, first you see a straight line region. You see that straight line region here? That's where stress and strain are directly proportional to each other. That's called the elastic region. And basically, actually, the Young's modulus is determined by dividing the stress and the strain in the elastic region. So it's a number. Each material will have a Young's modulus. Okay. Now, what is interesting for the steels, all the different steels have the same straight line region there, that same E value, like when you kind of taking the tangent of this angle, the stress over the strain. they all have the same modulus of elasticity. It's their ultimate tensile strength here, the UTS, the maximum ultimate load, that value there, that varies. If you, for example, if you put more carbon in the steel, it becomes harder, okay, and stronger. Now the only bad thing about it is it also becomes more brittle, okay. So you lose ductility or plasticity, the formability of a material. When you add more carbon, you get more strength properties, but your ductility goes down. See, like this whole region here, this is the elastic region, just this little region. All this is plastic deformation until finally it breaks here. Now you might be going like, how could that be possible that this value here is higher than when it breaks? Well, that's because we're really doing a test incorrectly. We're doing what we do is when we calculated the stress, we were dividing by that original area, right? And we kept dividing by A0, and it really is changing all the time. But for simplicity, people do that. They call it the engineering stress strain diagram versus the true stress strain diagram.
So you should divide.
You should really divide by the instantaneous area when it's constantly changing. But that's more, you know,
that's more mathematical than
people don't
apply.
Yeah. Now there's some people there's graphs like that, but the documented tables always have these values in there, like the ultimate tensile strength dividing by the original area, the way we were showing you. Now, what you see here is kind of strange on a lot of steels. You will see supposedly an upper yield point and a lower yield point. So it's kind of like you get this, here's where the elastic region basically ends. Then you go a little bit more, and then it actually goes down without increasing the stress, and then it starts to go up again. Now, in our lab, with our old testing machine, I have never seen this, and we have done many, many graphs. So I don't know if our equipment that we had was not good enough, or what the case is. It's really odd, you know. I'm hoping to see this on the new tensile testing machine, that we can maybe get a better resolution and get better values. But what we always see is straight line, and then bang, we go up and down. I think you took the class before, right? And that's what you got to see. So yeah, they call that the proportional limit. That's the end point of the elastic region there. Okay. Now, okay, we mentioned here the yield strength, right? Here where the material starts to yield, okay? And for a steel, we supposedly have kind of like a little stable area there, for almost like horizontal area there, and then it goes up. A lot of materials will not have that, and it just, you will see the straight line region, so that's the elastic region, and it starts to curve away, goes up, and then eventually it will break. Well, we're really interested usually in that yield strength value here. This yield strength value is a tabulated value for materials. Now, why is that such an important value? Well, see, if you design a chair, okay, let's say this chair was made out of metal, right? Then you want that chair to be strong enough so it doesn't deform, right? So you want it to stay in what region? The elastic or the plastic region? Elastic region, right? You want to look at the loads that you have, and you want to keep the loads below the region where you would go into permanent deformation. Or if you cannot control your loads, you want to design your components big enough in size so that, you know, the area, so you can distribute the stresses, so the stresses will go down, right? So we can do that, you know, in for example, in SolidWorks, we have a software that we have in our class called Solid Modeling, like SolidWorks, and then computer-aided engineering. Dr. Salim teaches a class in finite element analysis, where you place loads on the material, you have different supports, and then you can look at the stresses in the material. If you see the stresses are too large, they are beyond the safety factor, then one thing you can do is you select another material with better strength properties, or you design your sections bigger, or put rounded corners on there instead of sharp corners. and reduce the stresses. Okay, but okay, this is something that you can do also is when you have an engineered stress strain diagram, you go straight line region and it starts to curve away. A lot of times what we do is to determine that yield point, which is an artificial point, okay, we use the 0.2% offset method, where you have the stress over here, you have the strain is listed over here, and you measure off on the graph that you have, right, you have an engineered stress strain diagram, you measure off 0.2%, okay? Well, 0.2%, 1% is 0.01, right? 100 something, so 0.2% would be 0.002, right? And then you mark that point off. This is enlarged, this picture, okay? It will be right at the beginning, but here you draw a line parallel to this straight line, and you intersect it with the curve here, and then you get your yield strength reading. Some people will use the 0.1% offset method, but most people will use the 0.2% offset method to determine that yield point that we were talking about, because that's when you're just in the plastic region. Okay. Now this is another test, for hardness testing that you can do on materials, okay, and compare. Different materials have different hardnesses, okay, and hardness and strength are directly correlated to each other. So the harder the material is, the stronger it is also. There's a correlation between that. Now there's many different types of hardness tests available. We actually can do what they call a Bernal hardness test. You see here in the Bernal hardness test, you actually use an indenter here. It's a tungsten bowl, like W, Wolfram, right? And it's a 1 centimeter tungsten bowl, very hard material. And then they apply a force from the top. And of course you make an indentation in the material. And you can use a little eyeglass with a scale, vernier scale on that. And you can measure the size, the diameter of that indentation. Hardness and strength are directly correlated to each other. So the harder the material is, the stronger it is also. There's a correlation between that. Now there's many different types of hardness tests available. We actually can do what they call a Bernal hardness test. You see here in the Bernal hardness test, you actually use an indenter here. It's a tungsten bowl, like W, Wolfram, right? And it's a 1 centimeter tungsten bowl, very hard material, and then they apply a force from the top, and of course you make an indentation in the material, and you can use a little eyeglass with a scale, vernier scale on that, and you can measure the size, the diameter of that indentation, and then you can determine the area, and then you do load divided by area, and depending on what the load was, you get a Bernal hardness number, okay? And of course, the softer the material, the larger the indentation. The harder material, the smaller the indentation. You keep it for the same time period and all that. So that's one type of hardness test. Over here, you see a Rockwell hardness test. That's just another way of doing it. Rockwell is very common, and they use an indenter there. They have many different types of indenters there, and it works a little bit different. They apply a minor load, and then a little bit later they apply a larger major load, and then they measure the difference between the indentations. The machine does it automatically for you. Okay? And we'll be able to do both this summer, Bernal hardness test and Rockwell hardness test. So you'll be doing that. And here is the other hardness.